No, I think it's.
That's.
Yeah. It's, You're taking a look more comfortable.
Or do you have a?
I probably
Yeah.
just stand back here. Like when I'm
No, like I was saying. Okay, everybody, good morning. Welcome back. It's good to see that you survived so far. No major accidents. So first of all, some of you may have peeked, there's some t-shirts coming your way, but you will get them tomorrow. So incentive to stay the whole time. And then the other thing we're going to hand out at coffee break is this. Okay, you want one of these? You can ask Nick to sign it. Okay, so I think when we have coffee break, I'll announce it from down here. Okay, so we continue. Today's the last day of the practical training. Same format as yesterday. After lunch, we're going to have a discussion period instead of a lecture, where we're going to talk about whatever you like, about career advice, things about faculty and other careers, setting up labs, money, funding, all that fun stuff that you don't think about until you get to a higher position. Okay, so but before we get there, we're going to hear some great talks. The first one today is from David Mandrus from UT Knoxville. Dave is, I think, has been coming to every FQM school since its incarnation. So yeah, it's the sixth one. So thanks, Dave, for coming again, and look forward to it.
I actually learned my way to the building now.
Yeah, he knows it. Yeah, he hasn't done this.
Make it to the building. All right, thanks, JP. All right, so I'm going to talk about what I call exfoliable materials. So these are the building blocks for those heterostructures that you've been learning about. And, there's lots of other things you can do with exfoliated materials, and we're going to talk generally about some of how the science has developed over the years. And so I'm from Tennessee at the university, and I'm also affiliated with Oak Ridge. And here's my group at the university. And here's a little bit about Oak Ridge. So there's a number of user facilities in Oak Ridge that you might want to visit at some point. We're like the world capital of neutron scattering. We have two neutron sources. One is called the Spallation neutron source, and one is called the Hyper Center for Neutron Scattering. So this is a reactor-based source, and this is the Spallation source. And there's lots of beam lines there. You can do all kinds of different experiments. Efren is a frequent visitor. I think you're on some committee, right? You lead a committee, or you're leading the Neutron Scattering Association nowadays. Is that right? Right. So you can have a local contact for neutron scattering, and we have a nano center with all kinds of nanosciences getting done, and also high performance computing. If you ever need some supercomputer time, that's a good place to find it. Okay, so one of the nice things about a talk like this is you get to be a little philosophical. So in general, I think you can look at, there's what I call three drivers of new science in materials physics. And this is just based on experience over the years. So a new theoretical idea can drive science. People want to test the theory. A new experimental probe can also drive the science. And finally, new materials can also drive science. And so if you want to make a big impact, you want to be doing one of these three. And so in this school, we're talking about new materials for the most part. All right, so I've been making materials for quite a long time now. And so when I was in grad school, big thing was the high temperature superconductors, the cuprate superconductors. And so these have been around now for over a third of a century. And so people have studied them and studied them and studied them. And sort of for the most of my career, these have been sort of the main problem lying in the background that everybody was trying to relate to. And our philosophy for making materials during that time was, we don't want to wait around for the theory. We were just going to get in the lab and do something. And so there's the peasant who wants to harvest in his lifetime cannot wait for the ab initio theory of weather. And so with cuprate superconductors, we still don't have a great theoretical understanding of those materials. We don't understand what's the magic about copper. There's a lot of things we don't understand about those materials. But, we have to continue. And so we move ahead on the basis of chemical intuition, various heuristics. This is just pattern recognition, structure property relationships. These are sort of the standard tools for how to think about making new materials. So in 2016, there was a nice workshop organized by the Department of Energy about synthesis science. A number of the speakers here were involved in this workshop. And during the write-up, they basically determined that exploratory synthesis will continue to provide the overwhelming majority of new materials for years and perhaps decades. This is in 2016. But speaking in 2023, I think things have changed since 2016 somehow. Topology has really taken over our field to a large extent. Not completely. It's mostly, right now, it's a mixture of topology and electron correlation. I think it's the sweet spot. 30 years ago, there were no theoretical predictions of new materials. Now there's more than we know what to do with. There's tons and tons of theoretical predictions of new materials. However, when you go in the lab and try to grow some of these, most of the time they can't be grown. Mostly that's because the people who do these predictions don't actually think about the thermodynamics of making materials. There's other stable phases that form before the phase that they're interested in. There's been a lot of high throughput calculations, and they've created these huge materials databases, all kinds of band structures. You don't have to. There was a period there where experimenters could actually think about doing their own band structure calculation. We can still, but it's easier just now just to look them up in the database. And finally, more and more experiments require extensive computational and theoretical inputs and circuit. And this struck me especially during working on these Kitaev spin liquids, where you have this just a very diffuse blob of scattering and some part of reciprocal space. And there really wasn't much you could say about that without extensive theory. And so the question is, have these changes, do these mean that we need to have a corresponding revolution in our approach to new materials? I don't have the answer to that today. I'm still stuck in the old mode. It's not obvious if there is a new mode yet, but there might be one coming soon that people in this room might pioneer. Okay, so for people who are just getting started making new materials, here's some good advice, at least advice based on some experience. Don't believe everything you read. Just because it's published in a journal doesn't mean it's right. You'll find tons of mistakes. There's tons of mistakes in print. Okay, so it might be right, but it might not be right. There's a lot of bad things published. So don't automatically believe everything. All right, here's another one. If you have a good idea, almost certainly somebody else in the world has that same idea. I almost can guarantee it. just the way that zeitgeist works. I mean, if you had this idea, chances are somebody else has it. So there's some reason that you have to move quickly. And science doesn't reward good ideas unless you do something with it. So just having the good idea is not enough. You actually have to do something. Get in the lab, write a paper. That's where the rewards come. And this is one of the nice things about especially growing single crystals is that you can kind of go after the low-hanging fruit. So the nice thing about, there's crystal growth and there's thin film growth. They're both good at different things. Thin films are wonderful. You can make super high quality materials, but it usually takes a long time to optimize all the growth parameters to get a really good quality film. Whereas you can get a pretty good crystal very quickly. So if you want to move quickly and try a lot of different materials, then you're better off, I think, with single crystals. Whereas if you want to study one material in extraordinary detail, you're probably better off with like an MBE grown film or something like that. Okay. What is an exfoliable material? I don't know if the sound will work. I can try to try it out. So there's a nice video about how you prepare graphene. And I'll just see if I can make the sound work, but I don't know.
Take a Scotch tape and gently lay it down on flat surface. Next, take clean metal tweezers and pick a thin graphite flake, and then place this gently onto the Scotch tape. Next, fold the Scotch tape at the edge of the graphite plate. Peel it off gently, and do this step several times until you obtain a nearly transparent region on the Scotch tape. After this, take a clean silicon wafer to transfer the Scotch tape graphene onto the wafer. Use plastic tweezers and gently rub the area of the Scotch tape where graphene may potentially be. Slowly peel off the Scotch tape so as not to break any potential graphene sheets. Use an optical microscope to view and find graphene. Graphene appears as a purple spot on the screen. At the center of the screen is multi-layer graphene, and at the right corner, lower right corner of the screen is single layer graphene.
Okay, so that's how easy it is to make graphene. And there is a roll of Scotch tape in the Nobel Museum. True story. So one of the reasons that graphene research took off is just one of the reasons is because it is so easy to get started. Right? Anybody can take a piece of graphite and try to make graphene. So it's really been a revolution in science just because of that. It doesn't require a lot of expensive equipment. People can. So it started with graphene, but then it quickly moved on to some other materials. And so we're going to first talk about single layer materials. And so here's, we have the author of this article in the audience. He'll be giving a talk at some point. Maybe already talked. But so the first really big breakthrough after graphene was this MOS2 paper, where they showed that single layers of molybdenum disulfide have a direct gap, whereas multi-layers have an indirect gap. And so this was incredibly important result, because direct gap semiconductors are much more interesting for many applications, such as photovoltaics and so forth. Their efficiency in capturing photons is much higher. And so this really was a big breakthrough. And so people started studying all kinds of single layer materials. People made FET devices out of them. And you could switch them on and off. And so these were real semiconductors rather than graphene. Graphene is a semi-metal. And so it's not the most efficient for making electronic devices. These are semiconductors. There were lots of materials that form these two-dimensional transition metal dichalcogenides. So here's the chalcogens over here, sulfur, selenium, and tellurium. And they have various metals here that are colored that form various phases. So they typically form in layered structures. These are called van der Waals materials. This space in between here is called the van der Waals gap. Typically, your metal ions have two types of coordinations, octahedral and trigonal prismatic. And here are the three common structure types, 1T, 2H, and 3R. And it's just a slightly different stackings and coordinations. In terms of the physics, they're all, highly two-dimensional with these van der Waals gaps. All right, so there's tons of these materials. And this is an early paper. There's thousands and thousands of two-dimensional materials. And theory is great for predicting these because they could predict things like cleavage energies, right? So you want something that's very easy to cleave, has a small cleavage energy. That can be calculated. And so most of these things have still not been investigated yet, but this is just the tip of the iceberg. There's thousands of these things. And what attracted me to these systems was that they're really a bridge between both quantum materials and nanoscience. You have these few layer materials, atomically thin materials. So there's some new degrees of freedom available, like the layer degree of freedom. How many layers there are, that's a new degree of freedom. And they're very, very tunable materials, right? So you can stretch them, you can gate them, all kinds of ways to tune the materials. And so a few years after people started studying these transition metal dichalcogenides in single layer form, the idea that, well, maybe we can make magnets in single layer form. That also what came about. And so the idea here would be you'd have some sort of a chalcogen layer and then maybe a magnetic layer and then a chalcogen layer and a van der Waals gap. So it would be very similar, but it would have magnetic ions. And the goal, one of the goals of spintronics is to be able to control magnetism with electricity, right? So the idea would be if you could maybe make a device and you could gate the magnetism, you could control the magnetism of the gate voltage. That's sort of the thing that would get everybody excited. And so here's one example of that. So this material is actually magnetic. It's magnetic, but it's also metallic. And you could control it. You could switch it from a paramagnet to a ferromagnet with a gate voltage. So we worked on chromium, silicon, tellurium 3 quite a bit. It's a very easy to cleave material. It's also ferromagnetic. It's a semiconductor.
Next question, sure. So easy to cleave is of course a complex question.
Right.
But just in general, do you have a feeling for how many of these two materials are amenable to Scotch tape exfoliation?
So you can look that up actually. So you can, so they calculated the cleavage energy of graphite.
I don't mean how easy it is to pull the layers apart, but
It's actually
what's amazing to me about the Scotch tape on the graphene is, when you push that thing down with tweezers, that's enormous forces on the graphene that survives, right? The layer doesn't break.
You're talking about the whole process.
Cogenite or these other materials, I'm sure they're not as we know they're not as strong as graphene. And so if you try to apply the same approach do easy cleaning.
Yeah, I think most of them will work to some extent, maybe not as well as that. At least that's been my impression.
Must be more sensitive.
It's probably harder. It's probably harder in a lot of ways. And a lot of them are air sensitive. That's also a problem. So what happens is that everybody ends up working on a relatively small number of materials. So there's not a lot of, I showed you that big list of materials. But even today, that list is 10 years old. Even today, that list has been barely explored. Because everybody typically just works on the same apples materials. Probably just for there's a lot of learning. There's a learning curve, right? So learning to work with a new material. So here's this was the chromium germanium tellurium-3 instead of silicon. Chromium germanium tellurium-3. And Cheng Gong is a professor here at the University of Maryland Electrical Engineering Department. But he pioneered this measurement. He found single layers to be ferromagnetic. And probably the most famous magnetic one is this chromium iodine 3. And this was seen to be, they could see a nice hysteresis loop in one layer. They could analyze, they could see that the magnetism changed a little bit in 2 layers. Then it was, even kind of more similar to the 1 layer and 3 layers. All this stuff was worked out over the last 2 years. So yes, magnetism does exist even in single layer materials. Here's an antiferromagnet. Also interesting. It's another set of materials, like a transition metal, phosphorus, trisulfide. Those are also quite common. So here's one that we've worked on, ruthenium trichloride. So this one is close to a Kitaev quantum spin layer. It's not exactly there, but it's quite close. It has very strong Kitaev interactions. But it's also a highly cleavable material. And Arnav, I don't know if you guys know Arnav, but he's at Purdue now. He was a postdoc at Oak Ridge when he did a lot of this work. But so this one cleaves pretty nicely. And actually it's relatively stable in air. So one of the things about metals and narrow gap semiconductors is that they tend to form this amorphous oxide layer when they're exposed to air. So a lot of these are hard to work with in terms of single layer materials. Something you always have to watch out for. And a lot of the developments in recent years has been learning how to handle these issues, how to prepare devices without exposing the layers to the atmosphere. Here's an example of how they made a niobium diselenide superconducting flake. So you basically protected it with some boron nitride. They kind of had this polymer stamp here, boron nitride. They kind of did all this in the glove box. And they made some leads and everything without letting it see air. So it gets more complicated when you have to worry about issues, but it's still doable. All these details have been worked out now. Okay. So another thing you can do with these types of materials is intercalate other ions in between the layers in that van der Waals gap, right? So one of the most famous cases is this one. This is potassium carbonate. So this is, you can put potassium in between layers into graphite. So potassium will intercalate in between layers of graphite, and it gives you a superconductor with a low TC of 0.14 Kelvin. So when carbon-60 was discovered, I mean, probably a week later, Edward was doping it with potassium to see if he could make a superconductor, and he did. In this case, it's at 19K. And And so, yeah, so that was, you know, he knew about this work. So this potassium intercalated graphite was done, and that was kind of work that was done in the early 80s. And then 10 years later, everybody, at least I remembered it, when C60 was discovered. So here's another system where you can intercalate lithium into the van der Waals gap, right? You have a van der Waals gap, you put lithium in, you can make a 12.5 K superconductor. Story of the screw. Here's another case. This is the sodium X cobalt O2. So what you have to do to make this superconducting is you have to remove some of the sodium and replace it with water. So, it's kind of a watery superconductor. And I wanted to tell you this story of the screw. So we were working on this at Oak Ridge. This is, I don't know, maybe 2003 or something, 2004, right after the. And so what we wanted to do was, instead of H2O, we wanted to put deuterium, right? D2O. Deuterium is friendlier for neutron scattering. To do a neutron scattering experiment. And so at that time, we were not allowed to order any new D2O for whatever reason. It was some dual use item or something. But we found an old bottle of D2O lying around somewhere. And so we made some of this with D2O instead of H2O. And a collaborator of ours was looking at it. We found this tiny, tiny little magnetic signal. And he ended up wasting a lot of time, because what happened was there was a screw that had fallen into that bottle of D2O. And that was enough. Just a screw in the bottom. It was a stainless steel screw. It wasn't anything. We didn't notice it. But that was enough to give a little magnetic signal to the watery superconductor. So that's how sensitive squids are, how careful you have to be. Yes.
How do you synthesize it? How do you get the water to go?
Essentially, what you do is you put it into some bromine. Basically, bromine eats away the sodium, and then water will just go right in, something like that. It's pretty cool stuff, actually. It was kind of.
Is it? I heard the story that is it Kava that discovered that? He had this on his desk. Just a humid day. It just sucks up water or something.
Really?
Yeah.
You know, Bob was working on these. I don't know what he discovered this. But yeah, I think that's right. I think the discovery was accidental.
It's somehow very easily fixed.
It picks up. I think that story is right. But it's sitting on a desk picking up water. People finding superconductivity. And then there were joke articles too. You know, they were dunking it in different alcoholic beverages. See whether, which beer gave the highest CC, so forth. These are all, I don't think they ever published in real journals, but they're all in the archive as we search it. So here's another material that we spent some time with that's quite interesting. So this is essentially niobium disulfide intercalated with chromium, and the chromium sits at special lattice sites. So this whole crystal structure becomes non-centrosymmetric. And so you've got this layered, so the exchange interactions are pretty strong and ferromagnetic in the planes. It's always listening. It's always listening. Did I say serious? I don't know. Okay. Yeah, so the magnetic, so they're ferromagnetic aligned in the plane. They're lying flat in the plane. And then because it's non-centrosymmetric, there's a Dolizinski-Maria term, and it forms this very long period Healy magnet. So basically a one-dimensional helium magnet. It's quite interesting, actually. So this has been studied pretty hard over the last decade or so. But that's another example of an intercalated material. So here's what's called the chiral magnetic soliton lattice. Essentially, when you apply a magnetic field, so you've got this, so here's the Healy magnet, right, at zero applied field. It's just the Healy magnet spinning around. And then if you apply a magnetic field parallel to the planes, you form what's this magnetic soliton lattice. So you've got essentially these patches of ferromagnetic regions, and these are the solitons. These are like kinks. So there's like a 360-degree domain wall there. And so you can control this periodicity with a fairly modest magnetic field, only a few thousand, maybe 2,500 Oersted or something. So yeah, so it's kind of cool stuff, actually. Okay, so something else you can fool around with these types of materials is something called ionic liquid gating. Okay, and the idea here, this is the cartoon. So after I explain the cartoon, I'll tell you why I don't think it's true. But this is the cartoon that we were all thinking about for a number of years. So you have a semiconductor. This would be your sample sitting on a substrate. You have a couple of electrodes, a source and a drain. Then you put a drop of ionic liquid on top of your sample. Ionic liquid just is a liquid with two types of ions, right? Positive. Okay, and then you can apply some sort of a gate voltage to the ionic liquid. And so the idea would be, so if you apply a positive gate voltage up here, your negative ions are going to move up here. Your positive ions are going to sit on top of your sample, and that's going to create a current density here, the very top layers of your sample. And maybe, give you enough electrons to conduct electricity. That's the idea. You can gate it, you can control the carrier density. So this cartoon was believed for a long time, but there's been a lot of experiments that show that there's actually more than likely in your experiment, there's chemistry going on. What you're doing is actually you can put some protons into your sample or remove oxygen. There's different things happening above and beyond what's going on. I mean, maybe there's an example. Maybe in pure graphene, this cartoon is more or less correct, but in most other materials, you're moving protons or moving oxygen. And so you can dope it, but it's not happening the way this cartoon says it is. And so this was used to produce some superconductors. And you can change, the behavior based on the gate voltage. Essentially, you're changing the, you're gating the carrier concentration. So that was very interesting. So they made a device out of tantalum disulfide, and they could change the phase diagram based on the gate voltage. And that was kind of cool. And so we tried to do something similar with ruthenium trichloride. We tried to make a device with ionic liquid gating, and it just failed miserably. We actually made it more insulating rather than conducting. However, this actually led to something interesting eventually. So this is Eric Hendrickson, who's at Washington, St. Louis. And so what Eric did, he wanted to monitor the magnetic transition in ruthenium trichloride by putting a piece of graphite on top of the ruthenium trichloride and then measuring the transport of the graphite and try to measure, what did the magnetic transition in ruthenium trichloride, how did that show up in graphene transport? And so what actually Eric discovered was that when you put graphite or graphene on top of ruthenium trichloride, you had charge transfer. you actually metallize the ruthenium trichloride. This actually became even more clear after Rosa Valenti's group studied this problem theoretically. And charge transfer occurs between the two layers, making the ruthenium trichloride electron doped and the graphene hole doped. That's pretty well understood. So that's actually a very interesting way of metallizing hot Hubbard insulator by putting it in contact with something. So that was kind of new too. And so that really motivated us to start growing graphite intercalated with ruthenium trichloride. So we've done some of that work. So you can actually, you have graphite and you can put ruthenium trichloride in. So we've made stage 2 and stage 4 samples. So we're still in the process of studying them. They're hard. It's hard to do good crystallography. We haven't really nailed down the crystallography yet, but the transport properties are pretty promising. Okay. And so, this graphite intercalation compounds, these were studied quite heavily in around 1980. This is a hot topic. There's lots of magnetic materials that can be intercalated into graphite. So one thing we're thinking about, maybe these can be used, and remember that gating device controlling magnetism of electricity. You can, if you have some charge transfer, you might be able to gate some of the magnetism of these systems. So that's kind of the motivation. Okay, next thing you can do is start stacking these things together. So one of the nice early experiments had to do with putting a piece of graphene on top of yttrium iron garnet, which is a ferrimagnet. And so they put some, and what they saw was that due to the proximity effect, they actually saw an anomalous Hall effect in the graphene. So this showed the ideas, maybe, proximity, how you can use proximity coupling. Maybe study some new phenomena. And then, of course, there were the ideas of this Van der Waals heterostructures, which you've heard a lot about this week. You can stack all kinds of materials, try to design materials from the bottom up. So here's so this is a few years old, this slide at this point. I'm sure it's even more, there's more capability now. But this was, I don't know, probably 5 years ago, state of the art at Columbia. And Columbia is one of the places where they solve a lot of the technical problems for working with for stacking materials that are air sensitive. But at least at one point, this was open to people who needed to use it. This was funded by the NSF and it was part of the ROCT. So in some sense, a user facility. And then we've heard of, I guess we've heard about magic angle graphene. That was a huge breakthrough now discovered. And fairly recently, Cornell team here in the audience, they discovered the quantum anomalous Hall effect in these intertwined moire bands. And when I was reading this paper, one thing that struck me is we tend to think about these layer stacking. We don't realize how complicated it is. So not only do you have those moire bands, but if you look here, this is plotting layer distance. Okay, so these layers are not just sitting flat on top of each other. They're actually, the distance between the layers is actually changing. Right, so you have places where it's 6.8 angstroms, places where it's 7.4. So it's really complicated. They're just not sitting flat. So that's something I hadn't fully appreciated until I saw it in this paper. And then so robotic assembly, that's a hot topic. Right? How can you take it? So maybe, have we heard about robots today?
Really?
Okay. Eventually, robots will replace graduate students. But it probably isn't gonna happen anytime soon. I think.
It's probably more expensive.
But I mean, there's, you know, the thing is, it's very tedious to make a good sample, right? Very hard. It takes a lot of work, kind of heroic efforts, I think, to make. And, you know, if you could get robots to help you, that would be great. So I know that there's parts of it that are, can be, I think you can buy like, transfer stages that are robotically controlled, but you still. It's really minds yet. So robots. Okay, so for the last part of the talk, I'm just going to talk a little bit about how you grow the material. Typically, these 2D materials are grown using a technique called vapor transport, or chemical vapor transport. Essentially, what you do is you seal your starting materials in a tube. You have both your reactants and a transport agent. And there's reactions going on at different ends of the tube. And depending on whether your reaction is exothermic or endothermic, you can have crystals growing on the hot side of the tube or the cold side of the tube. I think Efren will talk about all that stuff right after, and I won't go into that. So if your formation is endothermic, crystals grow at the cold end. If it's exothermic, they grow at the hot end. Common transport agents are halogens like iodine, bromine, chlorine, HCl, ammonium chloride. Lots of things. So typically, you want about 1 bar of pressure in the tube. You want to have enough transport agent to give you about a bar of pressure. And again, this is not a new, there's enormous literature on this, on chemical transport reactions. But there's a lot of things there's a lot of parameters you can tune when you're growing the crystals. There's a lot of tricks. So these are some of the tricks that we developed in our group over the years. Essentially, you don't want to transport things too quickly. There's some this crystallization temperature. You want to do quite a bit of empirical experimentation, I think. Quickest way to get there. Large crystallization chamber. Uniform temperature in the crystallization chamber. Large diameter tubes tend to work better. And you can have a smaller gradient if you use a larger diameter tube. So the student who spent the most amount of time growing these things was Amanda. She's the one who put together most of these slides for us. So essentially, some of the tricks, you want to grind everything together, make it into a pellet, and press the pellet. And so you want to put it into a silica tube, but you want to keep the bottom of the tube cool if you can. You can put it into ice water. I think she just would wrap it and put a wet paper towel around it, I think. You could put it in liquid nitrogen if you really wanted to. So you want to form your starting compound. Then you can grind the sample. Make sure you have single phase. And start the vapor transport. So one trick she has, essentially when you're putting powder in a tube, you don't want the powder to coat the sides of the tube. It makes it hard to seal the tube properly if there's any kind of powder on the side. So you can use like a weighing paper or something to kind of make a little funnel for your powder, so your powder can get to the bottom of the tube without coating the side. That makes sense. So that's a nice trick. Again, she uses just a wet paper towel, but you could use ice water or anything. Keep that. So you don't want to volatilize anything down here. You want to keep it cool where you're sealing the tube. Yeah. So if you have a 2-zone furnace, that's great. But you don't need a 2-zone furnace. If you just have one of these like little mighty mites or mini mites, whatever they're called, they're cheap. They're like $1,000. Those can work too. You just have to calibrate it a little bit. This is the mighty mite. So you can calibrate. You essentially want to measure basically the temperature gradients inside your tube furnace. And then you can put the tube into a known temperature gradient, essentially. And you can control by using pieces of fire brick, like in the holes over here, you can control the gradients here. So you can use a thermocouple and measure the gradients. And you can prop the tube up on a couple of fire bricks, put it in your gradients. Yeah, I'm just there. And crystals will grow in too. It's pretty amazing, actually. Because it's, you just leave it alone for a week or two. Stop. And then there's some various things that can be happening that you don't want to happen. So if the crystals are growing slowly, you can add more transport agent or maybe increase the temperature. You can try to clean the inside of the tube with nitric acid. Maybe reduce the number of nucleation sites. Sometimes reverse heating. In other words, you change the direction of the gradient for a while and then you reverse it to the direction you want. Sometimes that helps too. And here's a bunch of stuff that Amanda grew. And that's all I have. Thank you very much.
Yes, Julia.
Thanks, Paul. I always enjoy listening to your perspective. I think it would be really helpful. Maybe get your perspective on how to decide what to make. I mean, you have to select this. I often wonder, especially if you look at circles, there aren't that many.
Well, it depends whether you want to. Okay, you're yes and no. You're right. Not that many systems have been looked at. However, there's huge databases full of potential material. So that doesn't mean they can all be grown. So the question was, how do I determine what the basically? So I think just in general, I think simpler is better. So like I'll tell students, like, let's say you have a choice of studying a material with 1 magnetic site or 2 magnetic sites. So you say, probably start with 1 magnetic site. If you can understand that, then you can think about adding another one. So you want to typically pick problems that are easier to understand. So especially for physics, right? Physics, we like easy problems and we want to understand them in depth. So it's easy to get into a situation where it just becomes a mess. So you generally want to pick easier problems and try to understand them more deeply. Now, in terms of the magnetism, the kind of things you want to look at is whether the moments are in the plane or out of the plane. What the domains might be doing. again, it's a lot of it is I need more detail about what you're interested in, but you have to be careful about what you work on, right? It's easy to waste a year working on something that nobody cares about. So you want to. There's this old saying too. It's like 6 months in the lab can save you an hour in the library. So you definitely want to see before you spend any amount of time on something. You really want to do a pretty thorough literature search. So the thing about making materials in physics, say, just finding a new material isn't good enough. It has to be something interesting as well as new. So what we're generally doing is starting from a known interesting material and not moving too far away, to be honest. Maybe we dope it in a certain way, or we make a small change from a known interesting material, thinking that that's going to be a higher likelihood of finding something interesting. We're not typically just branching in, going into the unknown without some firm rock to stand on. Does that answer your question a little bit?
Yeah, because not you all slow leaders. Everybody studying the same material.
Well, there does tend to be a herd mentality in physics, I think. Generally.
And you're right, I mean, the list, you don't want.
Yeah, no, I mean, simpler is better, generally.
But you don't, my clients are not simple, because,
No, nothing. If you start looking at it closely enough, nothing is that simple. But I'll give you an example. So, these high entropy oxides are pretty high. So people are putting like 3 or 4 different magnetic ions into the ion. And I'm trying to describe, saying, well, what can they possibly learn? That's why it just becomes. I mean, it's magnetic, but I'm not sure you're really. I mean, it just becomes messy. For example, or typically, there'll be magnets with a rare earth site and a transition metal site. And so if you have a rare earth and a transition metal, most of the time they just don't even talk to each other much. The transition metal will order at some higher temperature, and then the rare earth will order at lower temperature. Not much physics there. Sometimes there is physics there. I don't know.
Thank you for that interesting talk. So at the very beginning, you talked about this transition from exploratory mode to maybe something else. And the first element in your evidence that maybe there's a transition to a new mode was the shift to topology from electron correlation. I wonder what why that was connected with moving away from exploratory.
Well, okay, that's a good question. So really what's happened. So quantum material. So we call everything quantum materials now, but it used to be called strongly correlated materials or strongly correlated electron systems. And so what happened was around, when topological insulators came in, these were all on sort of like bismuth selenide and things like that. These were not strongly correlated materials, and they were amenable to sort of density functional theory, and so a lot of our people that were working on strongly correlated materials moved over and started working on topological insulators. And so that's why the name quantum materials came about. It was kind of topological materials plus strongly correlated materials. It was more of a sociological term, I think. It's like, okay, you have these people who are interested in these systems. What do we? They're not all strongly correlated. So But topology, it's not that easy to develop intuition about topology. You know, we can try to develop it, but at least I'm having trouble developing. I think without doing a calculation, it's very difficult to tell how topological something is, or whether, even with a calculation, I still don't know how we do. But yeah, I agree with you. I think they somehow do go together. This emphasis on topology, I think it has emphasized the role of theory even more than it has been in the past. You know, when cuprate superconductors were the paradigm, you know, theorists felt rather modest. So, but the theorists have been unleashed now. So we need to find something to put them back in their place. Something equivalent to a cuprate, where nobody really understands it very well. But you know, with topology, you know, there's a yeah, no, it's quite theoretical, very abstract. I don't have a lot of, at least personally, I don't feel I have a lot of intuition. So yeah, so if you want to try to find a new strongly correlated topological system without theory, how would you do it? I'm not sure how to do it. I would have to, you know, start looking at various calculations. Start with.
Last question, sure.
When you said at the beginning of the decade in 2010, there was hardly any predicted materials. And now at the end of the decade, there's many to work with. Exactly like how many materials have been predicted and how many of them have actually been made? If you know.
Yeah, so I would say thousands have been predicted and maybe 10 have been made. But again, that's just anecdotal evidence. I don't have a real. But my sense is that it's very, very easy to predict some new material that is stable at the density functional theory level, but that it cannot be grown in the lab. Yeah, I don't have any real knowledge. I don't think anybody knows the answer to that, to be honest, because you know, there's a lot of the databases that you can find. A lot of those materials in the databases are just theoretical materials, right? They're not actually real materials. Nobody's actually grown them.
Scary, really.
But yeah, no, it's all right.
Okay, all right, thank you, Dave.
Sure.